First, I would like to thank Guillerminus for his invitation. This is a great conference, and we have so many exciting speakings. My talk is robust locking Ochinikev superfluidity in laser-assisted bilaser Fermi gases. I come from Capital Normal University, which is the key university of Beijing City. As a major normal university, CNU has learned a high reputation among the general public. Currently, over 50% of the principals and a large number of outstanding teachers in Beijing's primary and high schools graduated from CNU. These are the collaborators, and here is Guillerminus, and these two professors are my colleagues of CNU. This is the outline. First, I will introduce the history of the FFLO state, and then I will introduce the spin optic coupling, which can induce the FF state. After that, I will introduce the pseudo-spin SOC in laser-assisted bilaser system. And finally, I will show that the LO superfluidity can be realized in the laser-assisted bilaser Fermi gases. So the FFLO state with the finite pairing momentum has been played important roles in understanding the various physics in many systems, ranging from the condensed matter to nuclear physics. In 1964, Ford Ferrell first introduced the state, the superfluid state, with a single pairing momentum. Now, this state, in a spin polarized system, this state preserved the translational symmetry. And later, Larkin and Ochinikev generalized state to a new state with a parallel pairing momentum. This state has off-diagonal long-range order and has a long-range density order simultaneously. And this state possesses the supersolid properties. So, although FFLO state has been predicted more than half a century ago, until now there was no direct experimental observation. In 2006, several groups have paid a great interest in studying the spin population imbalanced system. In this system, however, since the population imbalance suppress the fluid order parameter, this makes the FF and the LO state easily destroyed. Recently, the realization of the spin optic coupling has attracted enormous interest. By using the two-photon Raman processes, these two spin states can be transit. At the same time, it will induce a momentum transfer, resulting in the effective one-dimensional spin optic coupling. And until now, and currently, the spin optic coupling has been realized for both Einstein condensate and the Fermi gases. This is the spectrum, and which is symmetric. If we add in-plane magnetic field into the system, this is energy spectrum. The spectrum will be deformed. And since this is the Fermi surface, in this case, since the Fermi surface is mismatched, and we will find that a finite pairing between these two sides, a finite pairing of the FF state. FF state can be predicted. This is FF state. However, for alkali atoms, the two-photon Raman process causes heating effect due to the fine structure splitting resonance of D1 and D2 lines. This makes the study of the many-body physics becomes a very hard issue. To overcome the heating problem, there have been some other schemes. One scheme is to use the alkali earth atoms, which have the ground state angular momentum. In this case, we can use a single photon Raman process to directly couple the ground state to the excited state. And very recently, Keller Group has addressed a new scheme for bosons to realize the pseudo-spin SOC. This is the scheme. And this scheme uses a double wire potential, and the atom states localized in each wire, playing the role of the pseudo-spin. And then this is the laser-assisted tunneling. It will induce a momentum shift in the in-plane direction, resulting in the effective the SOC. In this scheme, the heating can be strongly suppressed. At the same time, we have done the similar theoretical works. Generally, we consider N layers of Bose-Einstein condensates. And these are the laser-assisted tunneling. It will induce the in-plane momentum shift. This is the N layer. If we consider N layer N equals 2, this is reduced to the same model of Keller group. And this is the phase diagram. Using this scheme, the strap phase with super-solid properties has been observed in Bose-Einstein condensate. And the strap phase has been predicted for 4 years, but the early experiments had some difficulties, so the direct observation of strap phase has not been reached. Now, this is the experiment. In the laboratory, here is the double layer Bose-Einstein condensate with the ground state in the 0 state. Now, due to the interlayer tunneling, it will induce a new pairing momentum in each layer. And then this will result the spatial modulation. That's the strap phase. This is the modulation of the order parameter. Here is the experimental phase diagram, and the superfluidity of the straps can be detected via Bragg scattering in experiment. So this is for Bose-Einstein condensate. So our question is, what would happen for fermions? We consider the two layers of the two-component Fermi gases with the spin up and the spin down. And this is the laser-assisted tunneling. It will introduce the in-plane, the momentum shift in each layer. And then after the gauge transformation, we can arrive at the effective Hamiltonian. And here, kappa is the momentum shift along each layer. The first layer is plus kappa, and the minus layer is minus kappa. The second layer is minus kappa. And here, J is the strength of the interlayer tunneling. And as we know, for the two-dimension or crystal two-dimension, there always exists a bound state. So this is the S-wave attraction. The S-wave attraction U can be renormalized by the bound state EB. Okay, so here we should stress that different from the real spin SOC. There are no pairing interactions between the two pseudo laser states. The laser states, there are no attracting interaction. So, and the interplay between the interlayer attractive interaction and the laser-assisted interlayer tunneling of the atoms can provide integral physics. Okay, since as I have addressed, since the pseudo-SOC occurs between the laser states, so there is no mixing between the spin singlet and the spin singlet and spin triplet. So we can construct the wave function of the bound molecular state in the singlet space. Okay, this is the main result. We can see that a bound molecular state appears This is the energy spectrum has a double minimum with finite momentum. Okay, this minimum momentum will decrease with increasing J and finally become 0. Okay, we found that this EB represents the interaction strength. So with the increasing of the atom interaction, we find the critical strength, tunneling strength will increase. This means that the stronger atomic interaction will favor the formation of the finite momentum bond molecular state. So the implication of the two-body results is that when we consider the many-body ground state, the pairing instability of the underlying Fermi gas would happen at finite momentum. So we solved the ground state by the BDG equations, and here we found that obvious the strap modulation of the pairing order parameters appears. And this modulation breaks the translational symmetry and exhibits solid state properties. And here is the corresponding momentum distribution with two sharp peaks at the opposite momentum. And this is L states a fluid state, and we find that the spatial modulation becomes stronger for larger J. Here I should stress that compared with the FF state, the LO state is more interesting because it's the FF state preserves the translational symmetry. LO state breaks the translational symmetry. So the LO state exhibits the superfluid states. So this state is very interesting. So to understand the pairing of the LO state, we can first look at the small J, small tunneling length. In this regime, it can be considered perturbatively. So we can present a simple perturbative picture. So in the laboratory, when there is no tunneling, the two layers are decoupled. So in this case, the two layers are all the conventional superfluidity superfluid with zero pairing momentum. And then we turn on the tunneling, the interlayer tunneling. The tunneling will induce a new pairing momentum with 4 kappa. This kappa is from the transferred from the second layer to the first layer, and vice versa. In the second layer, it induced the 4 minus 4 kappa. So then the interference will result in the spatial modulation of the pairing order parameter. So for general J, we can understand the nature of the pairing by the Fermi surface topology. We show that for various Fermi levels, these are the atomic states of the first layer. Okay, we just projected the Fermi surface to the one of the layer. So we take the first layer for example. So these are the atomic states for the first layer on the Fermi surface corresponding to different Fermi level. So we can see that each layer, the first layer has 2 pockets. These are 2 Fermi pockets with different weights. So and this pocket, which has a small weight, comes from the second layer, transferred from the second layer by the interlayer tunneling. So our results show that if the J, the interlayer tunneling, the strength J is less than the critical value, the pairing occurs inside each pocket. When J exceeds the critical value, we find that the pairing occurs between the 2 different pockets, resulting in the total pairing momentum being zero. So that's the normal, that's the conventional superfluid. So this is the phase diagram of the order parameter and the pairing momentum. We can see that with the increasing of the tunneling length, the pairing momentum gradually decreases and then becomes zero across a critical value. So this defines the transition from the LO state. Define the transition from the LO state to the normal superfluid, which is characterized by the zero pairing momentum. So So we have explored both. Finally, we have explored both the BCS and the BEC sides, and find that the results are valid for BCS to BEC regimes. So finally, I make a conclusion. First, the laser-assisted SOC, which avoids the heating, have dramatic effects on both two-body and many-body behaviors. So for the two-body bound state, it contains a degenerate double minima structure, suggesting pairing stability of the underlying Fermi gas at a finite momentum. So finally, we provide solid evidence that robust LO state can be realized in these laser-assisted bilaser structures, which breaks the translational symmetry spontaneously and exhibits supersolid properties. So thank you for your attention.